Today, we shall be looking at some of the factors that we need to consider when we are interpreting laboratory results. Let's look at this graph. We have 12 subjects labeled A to L. They had blood tests performed on different days. We can see that each subject has different results on different days. The mean result is shown in blue. CVI represents the coefficient of variation within subject. We also see that different subjects have different results. The mean result of each subject is different. CVG represents the coefficient of variation within the group. We just remind ourselves of the formula for coefficient of variation, which is standard deviation divided by the mean. This is an example of within subject and group variation of cortisol and aldosterone results. The blood was taken at 8 o'clock in the morning on different days. The factors we need to consider are analytical variation, biological variation, and the reference change value. Analytical variation relates to what happened to the specimen when it reaches the lab. We have human factors to be considered, how the specimen is stored. For example, a specimen that is analyzed within a short time after the sample is taken is likely to yield a different result to a specimen that is stored for a day or two. Analytical variation is very much dependent on the concentration of the analyte we want to measure. The lower the concentration of the analyte, the greater is the analytical variation. This is a plot of coefficient of variation versus troponin I concentration using 4 high sensitivity troponin I assays. As you can see, as the concentration of troponin falls, the coefficient of variation increases. Biological variation is the noise that cannot be eliminated. It is present even after analytical imprecision and other forms of laboratory error have been minimized. It is the largest contributor to variability in laboratory results. It is affected by factors such as physiology, stress, mood, state of health, activity, and environment. The question is, how do we estimate whether the difference between two measurements is real or due to random variation? To do this, we need to calculate the reference change value. It is defined as the minimum change required to conclude that two serial measurements are likely different. The formula for calculating the reference change value is shown. If you want to learn more about biological variation and reference change of value, you may wish to watch these two YouTube videos. This is a table of common analytes. It gives the analytical variation, biological variation, and the reference change value of each analyte. Let's look at some examples. In this example, a patient with a total cholesterol of 5.5 millimoles per liter goes on a diet. After 3 months, his total cholesterol is 4.5 millimoles per liter. Is this a significant change due to his diet? I'm using an online calculator published on the British Medical Journal website to answer this question. The analytical variation for total cholesterol is 2.1%, and the biological variation is 6%. Applying the reference change value to a total cholesterol of 5.5 would give a range from 4.53 to 6.47. This means that the value of 4.5 is just outside the reference change value. It therefore means that this result is unlikely to be due to the combined effects of analytical and biological variation. Let's look at another example. A patient with heart failure with a creatinine of 115 micromoles per liter starts on an ACE inhibitor. His creatinine is checked after 2 weeks and is found to be 125 micromoles per liter. Is this a significant change? So the analytical variation for creatinine is about 1.2%, and the biological variation is about 4.5%. When the reference change of value is applied to the serum creatinine of 115, we find that the range is from 100 to 130 micromoles per liter. This means that the value of 125 is within that reference change value. In other words, it is not a significant change. Having said that, from a clinical point of view, we will be wanting to keep a close eye on this patient because his serum creatinine results are both abnormal. Let's look at this example. A patient with a hemoglobin A1C of 44 millimoles per mole has the test repeated a year later. It is found to be 48 millimoles per mole. Should the patient now be told that he is diabetic? The analytical variation for hemoglobin A1C is about 4.3%, with a biological variation of about 2.9%. If we apply the reference change value to 44, we find that the range is from 38 to 50 millimoles per mole. This means that the value of 48 is within the reference change value. Please note, however, that this is a high-risk patient with 2 hemoglobin A1C results that are abnormal. He will need further evaluation to decide whether he's now diabetic or not. The take-home messages are: number one, all laboratory measurements have a degree of uncertainty that needs to be taken into account when interpreting results. Number two, the reference change of value allows one to decide whether the change in the results of a test may be due to a combination of analytical and biological variations. Number three, biological variation is usually the largest contributor to the reference change value. Number four, as always, interpretation of test results also requires the clinical context to be taken into account. Thank you.